Welcome back to Galois theory sessions. We are going to discuss two special ideals, prime and maximal ideals today. Before jumping into the definition of these ideals, I want to discuss the motivation behind defining this. A ring is a generalized structure of real numbers, but it is so generalized that a ring doesn't need to have a division. Real number system has addition, multiplication, subtraction and division, but in a ring you don't need to have a division, meaning does not need to have a multiplicative inverse. So the objective of defining these ideals is to embed a commutative ring with unity into a field. Embed into a field. A field has got division, subtraction, multiplication and addition, all just like real number. So for this, the tools which we are going to use are this. One is the canonical homomorphism. Canonical homomorphism. What is this? We already explained this one. So if n is a ideal of R, then there are two rings here. One is R and one is R by n, the factor ring. And we can define a homomorphism like this. Phi of A is equal to n plus A, or that is equal to A plus n. This is a homomorphism with a kernel phi is equal to n. This homomorphism is again, this is also onto, it is surjective mapping. And for every element in R, we have an element here. So we can think about R is embedded in R by n. Because if you take any element here, for any element here, this is the corresponding element in R over n. So this is actually embedded in R. So if you want to embed a ring, we can consider a factor ring here. That is one way of embedding using a canonical isomorphism. Another result which we are going to use is a field does not have a proper ideal. The only two ideals of a field is the trivial ideal and the improper ideal. There is no proper ideal. So if you combine these two ideas, we want to embed R into a field. So how can you make a field? So we want to make R over this factor ring a field. So that is our objective. If you can make R over N a field, then we can easily embed any ring, any commutative ring with unity into a field. So let M be an ideal of a commutative ring with unity. Commutative ring R with unity. So now this is not any ideal. So choose this M such that R over M is a field. It may not be possible, but if it is possible, choose an M such that R over M is a field. Then what are the properties of M? You cannot choose any M and make this as a field. So let us consider. So what you need is you want to choose M such that it doesn't have any proper ideals. R over M should not have a proper ideal. It should have only trivial ideal or the factor ring itself. That is improper ideal. So that is, so if you choose that, if you choose such an M, then that is what we want, and we call that as a maximal ideal. Okay, and see how we are going to arrive at. So let us assume that let us assume that there is another ideal, a proper ideal that contains M and different from M. So N is actually different from M and N is different from R. So what happens here? So we can consider a homomorphism, a canonical homomorphism from R to R by M. This is a homomorphism, so it preserves the ideal. So phi of N is a proper ideal in R over M. This should not happen. If this happens, then R by M cannot be a field because phi of N is a proper ideal of R over M. So the condition what we want to have is R by M should not have a proper ideal. So if there is a ideal in R that contains a proper ideal in R that contains M, then we cannot have R by M a field. So what should be the condition? It is so for R by M to be a field, M should be an ideal such that there exists no proper ideal containing it. There is no proper containing it. In that case, R by M is a field. And that is a definition of a maximal ideal. An ideal M of R is maximal if there does not exist a proper ideal in R such that it contains M. So we'll start the definition of the maximal ideal. So the thing is, we want to make R over M a field. The only way you can do one is if you take another ideal containing M, then it cannot be a field. So M has to be the maximal, like there should not be any ideal containing, any proper ideal containing it. So let us define the maximal ideal, the definition. An ideal M in a commutative ring R is maximal if there are no proper ideal in R containing or properly containing M. Properly containing. So that is a definition, that's a formal definition. So what we have found is if R by M is a field, then M is maximal. That's a result which we just now proved. Now let us assume M is maximal in R. Then can we say that the factor in R over M is a field? That's what we want to find out. So suppose R by M is not a field. And what does that mean? If it is not a field, definitely will have an element that does not have a multiplicative inverse. Then let A in R minus M. It cannot be in M because if it is an M, then it will become the additive identity of this factor group, factor ring. So I am going to take an element from R but not in M, such that A plus M does not have an inverse, a multiplicative inverse. I am going to say inverse. So this is an element here. So we are going to construct an ideal using this element in R by M. How can we construct it? We can think of a principal ideal generated by this. So then A plus M is an ideal principal ideal generated by A plus M in R by M. This ideal contains 0 plus M. That is because 0 plus M is equal to A plus M 0. So this is an element in this ideal, principal ideal. That is the reason. And this ideal does not contain 1 plus M. The reason being because 1 plus M is a unit, is unity of R by M. So A plus M is a proper ideal in R by M containing 0 plus M. Now consider a homomorphism plus R to Rm. And homomorphism, ring homomorphism preserves ideals. Then it is an onto function, by the way, because every element of R by M has an element in R. So we can think about an inverse of this ideal A plus M. This is an ideal. I am going to be inverse. Is an ideal in R because this contains M containing M is a proper ideal. I would say a proper ideal. Because 1 plus sum, inverse of 1 plus sum is not in this. It's a proper ideal R containing M. So this contradicts the fact that M is maximal. We started with M is maximal and we found there is a ideal, proper ideal in R containing M, which is not correct. The reason why we arrive at this conclusion is because we assume that R by M is not a field. So that implies R by M is a field. So now we have a necessary and sufficient condition for an ideal to be maximal. An ideal M in a commutative ring with unity R, commutative ring R with unity is maximal if and only if R by M is a field. I will take a couple of examples. As usual, we take Z. 1, 2, 3, minus 1. There are several ideals for this ring. So any ideal of Z is of the form NZ. But not all the ideals are maximal. Let's take an example here. 3C and 6C. Both are ideals. This is actually 0, 3, 6, minus 3. This is 0, 6, 12, minus 6. So obviously 6C is contained in 3C and which is contained in C. So obviously 6C is not a maximal ideal because there is a proper ideal which contains this. But we will not be able to find another ideal in between these two. So 6C is not maximal. 3C is maximal because we don't have a ideal between 3C and C. And that is because 3 is a prime number. Because 3 is prime. So in general, PC is a maximal ideal where P is a prime number. See what happens if you take the quotient here. This is our R, this is our M. So if you take quotient, C over PC is isomorphic to CP. And CP is a field, definitely. It's a finite field. So that actually matches with our result here. This is our R, this is our maximal ideal, and when you take a quotient, you will get a field. So now we have a necessary and sufficient condition for an ideal to be maximal. So what is that? Let R be a commutative ring with unity and M is an ideal. Then M is maximal if and only if R by M is a field. So we defined maximal. Now next one is the prime. So what is the next option? If you don't have a maximal ideal, you cannot create a field here. But if you don't have a field, what is the closest option for a field? Integral domain. Because for any integral domain, we can create a field, and that field is called field of quotient. So it's okay if you get an integral domain from an R instead of field itself. Sometimes it may not be possible. So our next aim is choose M, an ideal, choose an ideal M, in a commutative ring R such that R by M is an integral domain. If you want to make R by M as an integral domain, what are the conditions you want to put it on the ideal? And that condition, if you apply to this ideal, then it will become the prime ideal. See what happens here. So we are assuming that R by M is integral domain. What does that mean? Take two elements, A plus M, comma B plus M in R by M. Then what is the definition of an integral domain? You multiply these two together. So that means A, B plus M. So the definition of integral domain is for any two elements A. Actually, what is an integral domain? Integral domain is a commutative ring with unity having no zero divisors. That means if you multiply two elements and is equal to 0, then either A is equal to 0 or B is equal to 0. So here, if this is equal to 0, meaning what? 0 is what? This is equal to M. If this is equal to M, because M is the 0 element of the factor group, then what happens? If this is equal to 0, then that implies either A belongs to M or B belongs to M. If A belongs to M, then the whole thing belongs to M. If B belongs to M, the whole thing belongs to M. So this is an element in M. So it will become M. So if you put this condition on the ideal, that is M is an ideal of R such that AB belongs to M implies either A belongs to M or B belongs to M. If this condition is satisfied, then R by M is an integral domain. And that is the definition of prime ideal. Now we will define prime ideal definition. An ideal N of a commutative ring with unity is a prime ideal if A B belongs to N implies either A belongs to N or B belongs to N. Now, we already have the sufficient condition, that is, if R by N is an integral domain, then N is a prime ideal. We'll see what happens if N is a prime ideal. Can we say that R by N is an integral domain? So we'll assume that N is a prime ideal. Then how do you prove a ring is an integral domain? Take two elements. So let A plus N, comma B plus N belongs to R by N. Then A plus N times B plus N is equal to AB plus N. So actually, what we want to prove is take two elements in ID, and if AB is equal to 0, then we need to show that either A is equal to 0 or B is equal to 0. So we have to prove that either A plus N is equal to 0 or B plus N is equal to 0. So if this is equal to 0, this is equal to 0 means this is equal to N. What does this mean? This means that here, this means AB belongs to N. If this is equal to 0, that means AB belongs to N. AB belongs to N by the definition of principal ideal. This means either A belongs to N or B belongs to N. That means either A plus N is equal to 0 or B plus N is equal to 0. And that's what we want to prove. So the next result is for a ring, for a commutative ring with R, ring R with unity, for a ring, for a commutative ring R with unity, an ideal N is prime if and only if R by N is an integral domain. So we have two conditions here. M is maximal if and only if R by M is a field. N is prime if and only if R by M is an ideal, is an integral domain. So these are the two important results of this section. And so before we conclude this session, I want to give you one example of prime ideal. Example. Take R is equal to C. This is a commutative ring with a unit. So is a commutative ring with unity. Then the ideal 0 is a prime ideal. Why? Because let's take this as equal to n. R by n is equal to z cross z over 0, and that is isomorphic to z and is a integral domain. So this is an example of a prime ideal which is not a maximal ideal. So here 0 cross z is a prime ideal that is not